The development of Earth's climate, from fireball to forecast our planet, has been many things. A burning rock, a frozen wasteland, a steamy jungle. Today, Earth's climate stands at a crossroads. To understand where we're headed, we have to know where we came from. This is the full story of Earth's climate, from its fiery origins to the modern age. The fiery beginning, Hadeon to Archeon, Eon, around 4.6 billion years ago. Earth formed from the dust and debris surrounding the young sun. The early planet was a hellish place, molten rock, tense volcanic activity, and constant bombardment by asteroids. Temperatures exceeded to 0 degrees Celsius. There was no oxygen, no oceans, and certainly no life. Volcanoes released vast amounts of gases like water vapor, carbon dioxide, ammonia, and methane, forming Earth's first atmosphere. The high levels of greenhouse gases created a thick, heat-trapping atmosphere, allowing the planet to slowly cool despite a faint young sun. As the surface cooled, water vapor condensed into rain, possibly for millions of years. These rains formed Earth's first oceans, setting the stage for the emergence of life. The first life and the Great Oxygenation. This led to the Great Oxygenation Event around 2.4 billion years ago. The first signs of life emerged around 3.5 billion years ago in the form of single-celled organisms, especially photosynthetic cyanobacteria. These microbes lived in colonies called stromatolites and began releasing oxygen as a byproduct of photosynthesis. For a long time, oxygen was absorbed by iron and other elements in the ocean, but eventually it began accumulating in the atmosphere. Oxygen replaced much of the methane in the atmosphere, dramatically reducing the greenhouse effect and causing Earth's first known global glaciation, a precursor to future ice ages. Snowball Earth hypothesis. Between 720 and 635 million years ago, Earth is believed to have entered one of the most extreme ice ages in its history, possibly freezing over from pole to equator. This snowball Earth period may have been triggered by continental weathering and a drop in CO2. Glacial ice reflected more sunlight, reinforcing the cooling in a positive feedback loop. Only intense volcanic activity over millions of years could pump enough CO2 back into the atmosphere to reverse the deep freeze. This thaw likely triggered a burst of evolutionary development, the Cambrian to the Mesozoic, climate stability and warmth. The Cambrian explosion marked a period of rapid biological diversification. During the Paleozoic and Mesozoic eras, Earth experienced long periods of warmth and elevated CO2. The Carboniferous period saw the formation of vast forests that pulled CO2 from the air and helped create modern coal deposits. The Mesozoic era, known as the Age of Dinosaurs, was characterized by high global temperatures and no polar ice caps. Carbon dioxide levels were 4 to 6 times higher than today, and sea levels were much higher. This warm, stable period supported massive reptiles, lush vegetation, and widespread biodiversity. CO2 levels fell gradually over the next tens of millions of years. Mass extinction and cooling, the End Cretaceous event. A massive asteroid impact near the Yucatan Peninsula 66 million years ago caused the fifth major mass extinction. Debris blocked sunlight, plummeting temperatures, and collapsing ecosystems. The climate cooled significantly post-impact, paving the way for the rise of mammals and new ecological systems. Homo sapiens evolved during this time, adapting to rapidly changing climates. The Ice Ages. Pleistocene epoch. With the onset of the Pleistocene, Earth began experiencing cycles of glacial and interglacial periods. These were driven by variations in Earth's orbit, axial tilt, and precession. Glaciers advanced across continents, then retreated. Sea levels dropped and rose by as much as 120 meters. Around 12,000 years ago, Earth entered a warm interglacial period known as the Holocene, which continues today. The Holocene and the rise of civilization. The Holocene's relative climate stability enabled agriculture, urbanization, and the growth of civilizations. Minor fluctuations included the medieval warm period and the Little Ice Age, but overall conditions remained within a habitable range. Human activity during this time began to subtly impact ecosystems, but didn't significantly alter. Now global climaton till the Industrial Revolution. Modern climate change. The Anthropocene. Industrial Revolution marked a turning point. Burning fossil fuels like coal, oil, and natural gas released unprecedented levels of CO2 and other greenhouse gases. Deforestation and agriculture added methane and nitrous oxide. Since 1850, average global temperatures have risen by about 1.2 degrees Celsius. The last 8 years have been the warmest on record. Glaciers are melting, sea levels are rising, and extreme weather is intensifying. Current CO2 levels exceed 420 ppm, the highest in over 3 million years. Scientists warn that if global temperatures rise more than 1.5 degrees Celsius above pre-industrial levels, feedback loops could trigger irreversible changes. However, efforts to reduce emissions, transition to renewable energy, and restore ecosystems offer hope. Conclusion: learning from the past. Earth's climate has shifted dramatically over billions of years. From snowball Earth to greenhouse jungles, from asteroid winters to ice ages, change is part of the planet's nature. But never before has one species altered the climate so quickly. Understanding Earth's deep climate history isn't just fascinating, it's essential, because today we are shaping the next chapter. And the choices we make will determine whether our story ends in balance or in breakdown.